Welcome back. In our last video, we just barely started, talking about how to go through a matched pairs t-test using the same example that we used for the matched pairs t-interval, right? So we've got our random sample of 10 men using an exercise device, and we're measuring their resting pulse rates before and after a 6-week period of exercise. We've got 10 of these gentlemen's before and after, so when we take that matched pairs difference, we've got 10 data values in our sample. We took the sample mean of those differences and the standard deviation of those differences. And we're trying to figure out if the sample provides evidence that the device affects the average resting pulse rates for men over that 6-week period. In order to do the hypothesis test, a matched pairs t-test, same basic steps as any hypothesis test. First, you state your hypotheses. So, it's identical to the one sample t-test. We've got our null and alternative here, where a population mean is either equal to a value or something else. We're using mu d here to represent the fact that this is matched pairs and we've taken a difference between two data sets. Again, the d isn't entirely necessary, but no matter what, you should be, when you state your hypotheses, define your parameter. So mu d is the population mean difference in pulse rate after minus before. This matched pairs t-test is going to be two-sided. This is a not equal to, because we're interested in whether the exercise noticeably increases or decreases the mean resting pulse rate of these gentlemen. So that's where we left off last video. I went ahead and wrote what the conditions are for the matched pairs t-test. You'll find they are the same as for the they're the same as for the matched pairs t-interval. So again, we've already checked all these conditions when we use this example to calculate the confidence interval. We need randomization, 10% condition, and we need our sample size to be at least 30 or the sample to be nearly normal in shape. So, for randomization, we took a random sample of 10 men, so we're good. 10% condition, these 10 men represent less than 10% of all men who could use this device. And our sample size is less than 30, so this is not met, right? We've only got 10 values of differences, but when we calculated the confidence interval for this example, we did find that the sample was unimodal, roughly symmetric, and pretty much free of outliers. So all of these conditions are met. So we should be able to move on to stating our distribution and the name of the test that we're going to be doing. We've seen here that all of these conditions to use a matched pairs t-interval, we're doing the matched pairs t-test. They're the same conditions as the t-interval. All those conditions are met. So, since they are, we know that the sampling distribution of the sample mean of the differences, x bar d, has an approximately normal distribution. Now, you'll notice for this step of a hypothesis test, I have phrased things differently pretty much every time. And that's because of all the steps of a hypothesis test, this is probably the one where there's the most leeway in what you say and how you say it, right? Whether the sampling distribution of the sample mean difference has an approximately normal distribution, that's great. I don't want that to confuse you or the grader that you're not going to be using the normal model here, right? This is a matched pairs t-test. So what I also include here is, because the population standard deviation, sigma d, is unknown, we will use the t model with 9 degrees of freedom. Right? 9 degrees of freedom because our sample size was 10. Degrees of freedom is n minus 1. So the reason we're using t, even though this has an approximately normal distribution, is because we don't know sigma. We don't know the population standard deviation of all possible differences. Okay, so we're using the T9 model to perform a matched pairs t-test for a mean difference. I think it's important to write that out at this stage. That way you know that your test statistic is going to be a t statistic. You know how many degrees of freedom you've got, so that when you need to calculate your p-value, you know how to put that in. Right? So, now that we've gotten all that squared away, I haven't gone ahead and calculated the standard error this time of the sampling distribution. You could do that there. Right? I just chose not to this time. And that's up to you. It's a stylistic difference. You can do it if you want. All right, let's calculate our test statistic. We know it's going to be t. So t is equal to, and again, mechanically the match pairs t-test is identical to a one sample t-test. So when we went and did that one sample t-test, how we calculated t, we took the sample mean minus the value in the null hypothesis and divided by the standard error of the sampling distribution, which was s over the square root of n. So really, this is still the formula. I do want to incorporate the notation that we're putting d's on all these things because this is still representing a difference between two data sets. So this is the sample mean of the differences. This is, I'll call this mu d naught. we're subscripting subscripts here. So this is still the value in the null hypothesis, but it's for the mean of the differences. This is the standard deviation of the differences, and that's the sample size of the differences. Same formula though, exact same formula. So let's plug in all these values. X bar d, negative 2.8, minus the value in the null hypothesis is 0. And we divide by the standard deviation of the differences, SD is 2.53, over the square root of the sample size is 10. And that is going to give us t equals negative 3.5. And I may have rounded quite a bit to get that answer, so if you got something somewhat different there, it should be pretty close to negative 3.5. That's our test statistic. So we still need to be able to find our p-value here. And we've done enough hypothesis tests. I think it's becoming second nature. Once you have your test statistic, draw that curve. T-curve looks just like normal. 0 in the middle. Negative 3.5 is going to be somewhere over here to the left. What area do we want to shade? Now, if you're reckless, you would just shade everything to the left because you know it's like an end. But in order to know where to shade, you always look back to the alternative hypothesis. What is it we want to prove? This is a two-sided test. So we've got to shade on both sides. So yes, we do want this area over here, but we also want the equivalent area on the right end, everything from positive 3.5 and up. So in order to calculate these areas, again, you've got a choice here, but we essentially want the probability that t is less than negative 3.5 or that t is greater than positive 3.5. That's what we're trying to find. So the way I would calculate that, I already know I'm going to be using the calculator here, TCDF. I'm going to find this area to the left and just multiply it by 2. So I'm going to use 2 TCDF. My lower is negative 9999. My upper is negative 3.5. And the degrees of freedom is 9. That should be all we need there. Lower, upper, and degrees of freedom. Remember, for normal CDF, you need lower, upper, mean, standard deviation, because mean and standard deviation are the parameters for normal. For T, the only parameter is degrees of freedom. So if we calculate that, we should get a p-value of 0.0067. If you wanted to check your work there, you could use, on your calculator, you could go to t-test, so stat, test, t-test, and you could plug in the numbers for each thing that I will put up here for you. Okay, so here's what you want to put on your calculator. If you want to use that to do the t-test to verify that this is correct, you go stat, test, t-test. Mu naught is 0. X bar is the negative 2.8. Sx is 2.53. N is 10. And mu is not equal to reflect our two-sided test. And you should get a p-value either 0.0067 or very, very close to it if you round. So, all that's left, decision and conclusion, our last step once we have our p-value. Remember, stating your decision and conclusion, those are two separate things. The conclusion is, does this sample provide evidence? That's when you answer this. Your decision is whether you reject the null hypothesis or fail to reject it based on your p-value versus the significance level alpha. So once you've got your p-value, the very next thing you should do is, based on this p-value, what decision do you make about the null hypothesis? Then you can write your conclusion to this question. So, decision first, with a p-value of 0.0067, we're comparing that to the significance level, alpha. Was that specified in this problem? Of course not. Why would I specify alpha? I never seem to. So, if we don't know what alpha is, we'll just assume it's 0.05. How does 0.0067 compare to 0.05? The inequality symbol that will go here, it's less than 0.05. So if our p-value is less than alpha, that is when we reject the null hypothesis. I cannot state enough how important it is at the end of your test to write this. To explicitly compare your p-value to alpha and say what you're doing with the null hypothesis. This is critical. It's so important. In Unit 6, early on, I would see so many people. They did this correctly. All the mechanics were right. P-values, test statistic, all of it. But then they didn't write this, and they just wrote, there's evidence of this. It's like, well, yes, but you're just saying there's evidence. What is it? It's this. It's the fact that the p-value is smaller than alpha, and that you're rejecting the null hypothesis. Okay, so don't forget to put that in. Do not leave it out. Now, once you've said this, you can make your conclusion. If we're rejecting the null hypothesis, that means there's evidence of something. There is evidence that, or evidence of, the exercise device affects average resting pulse rates for men over a 6-week period. I'm just going to Control-C, Control-V over here. So I literally just copied the language from the question in my conclusion. Yes, there's evidence of that, because the p-value is less than alpha and we rejected the null hypothesis. Now don't get cute. Remember how when we do confidence intervals, when we interpret it, I like to go the extra mile and say that there is like directionality involved and say that, oh, the pulse rates are lower after than they were before. When it comes to interpreting this hypothesis test, all we can say is that there's evidence that the exercise device affects affects the average resting pulse rate. Affects. I am well aware that our sample differences were negative. Almost all of them. And the mean is certainly negative, right? That would suggest that the pulse rates after are smaller or lower than the pulse rates before. That does not mean that we should put in our conclusion that the exercise device lowers the average resting pulse rate. Why? Why can't we say that? Because that's not what we tested. Our test was two-sided. Does the exercise affect pulse rates or not in either direction? If the test is two-sided, all you can say in your conclusion is, yes, there's evidence that the pulse rates were affected somehow. In order to say something like, there is evidence that the machine lowers average resting pulse rate, you would have to test this with a less than sign. It would be a one-sided test. When you calculate your p-value, you would have to use just this area, and then you could say that. Okay? But since this is a two-sided test, this is all we can say. So make sure that your conclusion matches your test. Okay? And the best way to do that, if there is a question that is asking what you want to show, just copy that language into your conclusion. Okay. So there's just one more question that I want to ask based on this test. Let's see what it is. Okay, last question. For this example, what does the power of the test represent in context? The power of the test. Okay. So maybe your mind is going towards that diagram with the two curves, and power was here in the lower curve. But before we get to what it represents in the context of this example, what is the interpretation of the power of a test in general? Remember, power is related to type 1 and type 2 error. Type 1 error is when the null is true and we reject it. Type 2 error is when the null is false and we fail to reject it. But what's power? Power is pretty much the goal of the test. Remember, when we do a hypothesis test, what we're really interested in is rejecting the null hypothesis, if we should. So rejecting correctly the null. That's what the power of the test represents. Power is the probability of rejecting the null hypothesis when the null hypothesis is in fact false. Okay? If you are thinking of that diagram with the two curves, remember power and beta, type 2 error, were on the same curve. Those two are what could possibly happen if you have a false null hypothesis. Type 2 error is when you make a mistake and fail to reject. Power is what happens when you make the right choice and reject the null when it's false. Okay? So that's what it means in general. So what does the probability of rejecting the null when it's false mean for this example? Well, the null hypothesis is that the true mean difference in those pulse rates is 0. So power would be saying that the true mean difference is not 0, that the device does affect the average resting pulse rates, given that that's actually true. So power is us saying the device affects those average resting pulse rates when in fact the device does do that. And so here we go. Power represents the probability of concluding that the exercise device affects average resting pulse rates, given that it actually does. And just to state one more time, You do not need to write exactly this to answer this question correctly. That's how I chose to phrase it. You can have your own way. Right? So I don't want you to write this down verbatim and think that you have to like memorize this response. No. There are many different ways that you can answer that correctly. So, matched pairs t-test. Mechanically identical to a one-sample t-test. The only difference is right at the very beginning, you have to know to take the difference of those two data sets if in fact you're given that raw data. If you're just given the sample statistics like this, treat it exactly like a one-sample t-test. The only difference would be something like your conclusion is not that the mean of a data set is or isn't something, but the difference in two is. Okay. So, that's everything for one sample T. And for chapters 22 and 24 of the book, that material is now concluded. You've got your one sample T interval and t-test, and you've got your matched pairs T interval and t-test. So all the material in these two chapters of the book concerns all of that. We're done with it. Those homework assignments, check those due dates in Canvas for them. But at risk of making this video even longer, I do want to start the next example. I just want you to get a taste of what we're going to be talking about next. Right? The rest of this video and all of the next will deal with this next example that we're going to start right now. Okay, near the end of the video, just introducing a new example, but this will give you a head start for tomorrow's video. Here we go. To study the effect of drugs called beta blockers on the pulse rate of patients during surgery, available subjects were randomly assigned into two groups. One group received a beta blocker, the other group received a placebo. The pulse rate of each patient at a critical point during the operation was recorded. Okay, so a little bit of an infatuation with pulse rates, so this is going to be another example on that, but we're doing something completely different here. So we have two groups of patients who have been randomly assigned. Some are getting this beta blocker, some are getting a placebo, and we are recording their pulse rate at a specific point during the operation. And here is the summary of that data. We don't have the raw pulse rates themselves, but this is a summarization for both groups. So for the beta blocker group, the sample mean pulse rate was 65.2, and we can assume this is also measured in beats per minute. The sample standard deviation was 7.8 beats per minute, and the sample size was 30. For the placebo group, they had a sample mean pulse rate of 70.3 with a standard deviation of 8.3, and there were also 30 patients in that sample as well. So, part A says the distribution of pulse rate in each group is not nearly normal. The use of two sample T procedures is still justified. Why? Okay. I want to focus attention on the second sentence here. The use of two sample T procedures is still justified. By T procedures, we're talking about making a confidence interval, and we're talking about conducting a hypothesis test. What this is saying is we should be able to do that with this data set. Two samples, even though the distributions are not nearly normal. So, I want to unpack this one piece at a time. Why are we using a two-sample T procedure here instead of the matched pairs that we just finished? Right? We can use matched pairs with two different data sets, right? Right? So why is this not a matched pairs example? Well, for matched pairs, if you recall, it either works on before and after, when your two groups are based on the same individuals, or if the individuals are somehow paired together, linked in some way. Is that the case for the patients in these two groups? Some are getting a beta blocker, some are getting a placebo. those appear to be two separate treatments. And the individuals are not the same. This is 30 patients, this is 30 different patients. Is there any reason to suggest that the pulse rate of someone in the beta blocker group and the pulse rate of someone in the placebo group are somehow related or paired? I don't think so. There's no reason to suggest that I can think of. So these samples, effectively, we can treat them as independent of each other, right? If there's no linkage, if there's nothing in common, then they're independent samples. So that's why this is not matched pairs. And that's an important concept for you to know going from this point forward. Because in its construction, matched pairs and two sample T are going to look the same. You're going to have two groups. And you're going to be comparing sample means. But you need to determine whether the groups themselves are somehow paired or whether they're independent. If they're paired, use matched pairs. If they are independent of each other, use a two sample T procedure. Okay, so that's set up to this question. But in order to answer this, we need to check all the conditions for a two sample T test or a two sample T interval. I don't think that's going to be too bad. The conditions for both the two sample T interval for a difference in population means, which is what we're going to be doing first in the next video, and the two sample T test for a difference in population means are the same. Okay, so for T, for everything T related, the conditions for confidence interval and hypothesis test are the same. You've got one sample, matched pairs, and now two sample. Okay, so these samples are independent of each other. It's reasonably assumed that they are independent of each other. That's why we're using a new two sample T procedure versus matched pairs. You might even see this written as two independent sample T, but two sample T implies that the samples are independent, because if they weren't, you'd be using matched pairs. So the conditions for both the interval and the test for two sample stuff are pretty close to what we already know. To verify the independence of individuals, we've got two different conditions here. Any guesses what they might be? First is randomization. But if you recall, back when we did two sample Z things with proportions, once you have two groups, and we now have two independent groups, when we check conditions, we've got to check them for both groups. Both groups. So this is randomization for both groups. Is this condition met for this example? We'll go ahead and check them right now. The subjects were randomly assigned into two groups. So yes. Okay. Remember, for randomization, if you've got a survey, then the sample itself needs to be conducted at random. But if we've got an experiment like this one, it's not that the available subjects need to be randomly chosen, but it's the treatment assignment that needs to be done randomly. And that's what the problem says is done, so that condition is met. The other condition that allows us to verify that the individual pulse rates are independent between patients is the 10% condition, same as before. Are we looking at less than 10% of the population in our samples? Well, our sample sizes are 30, and not that we know what procedure is going on here or how many people have that procedure done, but unless we have good reason to say otherwise, it's reasonable to assume that these sample sizes are less than 10% of the population of all possible patients for this surgery. 30 is likely less than 10% of all possible patients for this surgery, so that actually meets the condition for both groups at the same time. Okay, so these two conditions together, just like they always do, verify the individual pulse rates in this case are independent between individual patients. There's one more condition that needs to be met to verify that the sampling distribution of the difference in sample means is approximately normal in shape. And we know from all of the tests that we've done in the past, all the conditions we've met, this condition has to do with how large the sample is. And this does borrow from the one sample and match pairs T procedures. N has to be at least 30, or the sample itself, the distribution of the sample, has to be nearly normal. In the past, we've dealt with sample sizes that have been relatively small, so we've needed the sample distributions themselves to be nearly normal. But in this particular case, the question's saying the distribution of the pulse rates in each group is not nearly normal. So this part of the condition is not met. But we can still use the procedure we're going to use because, for once, we've finally met the large enough sample part of the condition. The sample sizes both have to be at least 30, and we just barely made it. And in general, when we're getting into these two sample T intervals and T tests, for this condition, I would be shocked if you weren't either given large enough sample sizes or if you were just told straight away that the sample distributions were unimodal, roughly symmetric, and free of outliers, or just approximately normal outright. Okay? I don't think you're going to have to take raw data values for both samples and make histograms of both, because that would take so long. So it's really important that you know the different ways this condition can be met, because chances are there's going to be something in the problem, either large enough samples or this is going to be specified directly. Okay? So this video has gone on long enough. It's taken quite a long time to record, so I'm sure even edited it will be long. And I apologize for that. But the last video before your quiz in Unit 7 is going to continue through and calculate a two-sample T interval from these samples. And you'll find that it's very similar to what we did for one sample. Obviously, the formulas are going to change because now we've got two samples, but what we've already learned will apply. So I'll leave it there. I will see you in the next video. Take care.